Welcome to The Explainer. Today, we're kicking off our brand new series, LLMs from Zero to Hero. And we're starting right at the beginning, going back in time, before the big LLM boom, to uncover the foundational ideas, the absolute bedrock that made everything we see today possible. So let's start with a really fundamental problem. Computers don't get language the way we do, at all. To a machine, the word king and the word queen are just, well, they're just strings of characters. There's no built-in connection between them. So how on earth do you teach a computer that these two things are actually related? You see, before this whole LLM thing took off, the first massive hurdle for AI was just figuring out how to deal with the sheer chaos of words. How do you represent their meaning in a way a machine can actually process? Right. This is the core of it. We see the word puppy, and we instantly get this rich concept of a young, playful dog. A computer just sees the letters P-U-P-P-Y. So bridging that gap between just seeing text and actually understanding meaning, that was the big challenge. Okay, building block number one. The first real breakthrough landed in 2014 with a concept that just completely changed the game for how we work with language. It's called word vectors. The main idea here, made famous by a model called GLOVE, that stands for Global Vectors, was to map every single word to a specific point in this giant, multidimensional space. You can kind of think of it like a star chart for language. Words with similar meanings, like dog and puppy, would be clustered close together, while totally unrelated words, like dog and car, would be light years apart. And this is where it gets really, really cool. Because it's a mathematical space, you can actually do arithmetic with concepts. So what do you think happens if you take the coordinate for king and you subtract the coordinate for man? Well, you're basically distilling the abstract concept of royalty. And then what if you take that concept of royalty and you add the vector for woman? The model is doing this crazy calculation, royalty minus maleness plus femaleness. And boom, the resulting coordinate, the point it lands on, is incredibly close to the actual vector for queen. It's just a brilliant illustration. All of a sudden, computers could grasp these complex relationships without ever being explicitly taught. This was a monumental leap forward. Now, what's really fascinating is how they did it. The GLOVE paper explains that they achieved this by analyzing how often words show up next to each other across a gigantic amount of text. By cleverly combining two different statistical methods, they found a super efficient way to build this entire meaning space from scratch. Okay, so that's huge. We've got a way to understand individual words. But, language isn't just a list of words. It's about sentences, about sequences. So how do we take this amazing new understanding and apply it to whole phrases and sentences? Yeah, the next big question was, how do you process a whole sequence of words and then generate a totally different sequence, especially when they might have different lengths, like when you're translating from English to French? So some researchers came up with this really elegant solution called sequence to sequence, or just seek to seek. It works like this. First, a network called an encoder reads the input sentence word by word, and it squishes the entire meaning down into a single numerical code. You can think of it as a thought vector. Then, a second network, the decoder, takes that one vector and unpacks it, writing out the new sentence one word at a time. Now, here's a wild little detail from their research. They found this simple, totally counterintuitive trick. If they fed the input sentence to the encoder backwards, the model's performance got dramatically better. It sounds crazy, but this little change made it way easier for the model to link the start of the input with the start of the output. So, this trick was great. But even with this clever hack, the seek-with-seek model had a major weakness, a critical flaw hiding right in its design. The problem was that one single thought vector. It became a bottleneck. I mean, imagine trying to summarize a whole complex paragraph in just one short sentence. You're going to lose details, right? You're going to miss some nuance. The model was facing the exact same problem. And they weren't the only ones who noticed. Another team of researchers came along and pointed right at this issue. They basically said, hey, we think this fixed length vector is the very thing holding these models back, especially on longer sentences. In the data? Well, the data proved them right in a big way. This chart, which is based on their findings, shows the translation quality of that basic model just plummeting as sentences get longer. The model was literally forgetting the beginning of the sentence by the time it got to the end. So this huge problem needed a completely new idea, a way to free the model from that single vector prison. And the solution they came up with was brilliant, a mechanism that actually mimics how our own minds work. Instead of trying to force everything into one little summary, they asked a revolutionary question. What if the decoder could look back at the entire input sentence, at every single step of the translation? What if it could decide for itself which of the original words were most important to pay attention to right at that moment? And that is the attention mechanism. It's almost like giving the model a little flashlight. As it generates each new word, it can shine that light back on the most important source words, no matter where they were in the original sentence. Just like that, the bottleneck was smashed. All right, let's step back and connect all these dots. We've talked about 3 huge ideas, and they all kind of exploded onto the scene around the same time, in the landmark year of 2014. These weren't just clever tricks. They were, without a doubt, the essential building blocks for everything that came after. Think about it. Word vectors gave models a fundamental sense of meaning. Sequence to sequence gave them a framework, a blueprint for handling tasks like translation. And then attention gave them a flexible, dynamic memory, letting them tackle real-world complexity. These 3 things together paved the direct path to the transformer architecture and all the incredible AI we see today. So if you take away one thing from this, it's that in just one incredible year, we went from the chaos of words to a real, structured understanding. We taught computers how to understand words as concepts, how to process them in a sequence, and maybe most importantly, how to focus on what really matters. And that leads us to a really crucial question, one that holds the key to the next massive leap in AI. Attention was so powerful, but what happens when it becomes not just an ingredient, but the only ingredient you need? We're going to explore that very question in our next explainer.